Okay, let's go ahead and get rolling. I think it's it. Yeah. There you go. Chemical physical properties and law of conservation mass. There's your joke for the day. Thought a dinosaur moved in a museum, but it was a false alarm. Did you get it, Mary Kay? I get it. I enjoy it. You don't have to enjoy it.
Wait.
I didn't get it till
All right. Extrinsic properties. First thing. Physical property that does depend on the size of what you got. So weight, shape, volume. All right. While you're getting that written down, I'm going to go ahead and make sure we get attendance in. Everybody.
Can we retake our quizzes if we want?
If we have time today.
Oh yeah. Do we have to take it in this class?
Yes. If you have study hall and you show up during study hall, that's totally fine. We have to take it in this class.
Yeah, could we come in during lunch?
Sure.
Eat our lunch in here?
Nope. All right, extrinsic properties. A physical property that does depend on the size of what you got. So if I've got a big hunk of iron versus a small hunk of iron, the weight, shape, and volumes are different. Most of what you study in a physics classroom is based off of extrinsic properties. You look at the weight of the objects. You look at their shapes and their volumes based on what physics they're following. We're really not going to unpack this too much. What we are going to do is look at the other half of it, which is intrinsic properties. All right, we'll get there here in a second.
I'm kind of right there. She said.
We good here?
Your weekend.
All right, I'm moving on. Okay, intrinsic. These are more important of what we're looking at because this happens inside of a material. Does not depend on the size or the amount. So if a hunk of iron versus a small hunk of iron, their intrinsic properties are the same. Could be the color, the melting of the boiling points. Those are all the same. Solubility. What is solubility? What is it, Hannah?
How something dissolves?
Dissolves? Absolutely. Does it have to be in water though?
No.
No, all right, if it dissolves in a liquid. Because some things will dissolve in water, some things will dissolve in a non-water-based system. We'll talk about those later. But solubility is, does it dissolve? By the way, I forgot to mention, I filled up the candy bucket this morning. Thing is ready to roll. We got like 10 different flavors of Dum-Dums, Smarties, and chocolate. You ready, Hannah?
Oh, yeah.
You got it ready again?
Okay.
Okay, all right. My throat's been really off today.
I'm not ready.
Okay then.
Over the sink.
Over the other sink, on the
It's right here.
I have a question.
Yes.
So I saw this thing and it was a beach dolphin and I wondered, is that bad for them because they breathe air?
Well, I mean, they breathe air on a certain
They
level.
They breathe air, absolutely.
Yeah.
But a
that's
beach dolphin will eventually not do well because it can't get food, and also its skin will dry out.
Okay.
It's a water animal.
What's a beach dolphin? What are you talking
It means a dolphin that's washed up on the shore. It's been beached.
Because I saw this thing that sometimes dolphins beach themselves because they're injured and they don't want to drown, something like that. So sometimes they beach themselves on purpose.
Well, maybe you show me later. Okay. Density. Density is an intrinsic because it doesn't matter how much you have. It will all be the same density. So if I've got a big hunk of iron versus a small hunk of iron, the densities will be the same. Just a phone over there, but bounceability. So if you have rubber, all right, a rubber tire, it doesn't matter what it's made out or how big it is, but it will bounce about the same. Okay? We're really going to unpack these intrinsic properties by looking at. See we go there. Okay. We'll come back here in a second. All right.
Oh, Lord.
Physical properties, physical changes. Tomorrow, I wasn't able to set up your demo for today. Sorry, I ran out of time this morning. I'll have your demonstration up for tomorrow. If the room catches on fire, we'll just all blame it on Savannah. Okay.
Deal. Sounds good.
She'll be the arsonist.
I get one.
Okay. It's probably one of my favorite demonstrations ever done. I just need to go buy, I forgot to go buy the one thing I need this morning
What is
for
it?
it. I need cornstarch.
Ooh. Do you think Mr. has this?
Maybe, but I just didn't have time to ask for it this morning. Alright, physical properties, okay? Physical properties are measured without changing the composition of the matter. So if I want to see what the properties of water is, we can measure the mass, we can measure the density, we can look at the color, all without changing what it is. It's still water the entire time. Okay? A good indicator is, did you do anything to try to change it for a physical property? Or did you just record what you see, usually using your 5 senses? All right? Taste is kind of up in the air on argument if taste is a chemical or physical property. I'm not going to, I digress. I'm not going to hit on those semantics. Okay? But the big part is physical changes. It's when the substance changes the phase of matter it's in, but does not change its chemical structure. So really easy one. If you take water and you get it really, really cold, it turns into ice. Is it still H2O?
Yes.
Absolutely. If you take water and you boil it, it turns into steam, but it's still H2O. Right? That would be a physical change. Right? If I take a piece of paper and rip it in half, it's still a piece of paper. Have I changed its shape or structure? All right. Yes. Can't really melt paper without causing it to change what its chemical structure is, but you can rip it in half as many times as you want. That's a physical change. Right. Same thing for iron. If you take iron, you got a hunk of iron, and then you melt it. Well, it's just liquid iron. It's still iron. I don't know if there's anything as gaseous iron, but I'm willing to bet there is. You can get something hot enough, it'll turn into a gas eventually. All right. Good here? Did you guys do this in 8th grade?
What?
Physical chemical changes?
I don't remember that because I didn't like teaching.
Okay. Well, probably won't remember this year anyways because you don't like your teacher now. Alright, chemical properties. Alright, chemical properties are measured by attempting to change the matter. Attempting is the key word there.
I thought you said we weren't going to do a lot of notes.
No, I said we're going to do a lot of stuff this week. It's jam-packed week. Alright?
Why? Why you gotta do that?
Because this is chemistry. If you want an easy class, go take ICP.
I would rather not.
Alright? We're going to measure chemical properties by attempting to change it. It doesn't have to change it. So a good example of that would be flammability. So if we want to see if water is flammable, what am I going to do to it?
Catch on fire.
I'm going to attempt to catch it on fire. Is water flammable? No. Alright? So for there to be a chemical property, you can attempt to change the subject, or attempt to change the matter. So if it's not flammable, what do we call that? Non-flammable. You just put the word non in front of it. And I already helped us out earlier with solubility. So, solubility dissolves in a liquid. If it doesn't dissolve in a liquid, we call it non-soluble. Tough stuff, right?
Yes.
Here's one people get mixed up a lot: flammability and combustible, or combustibility. What's combustible? Dawson, do you know? It explodes or implodes. All right, we're not going to talk about implosions until second semester, but it could explode or implode without a fire. Do you know an example of that would be?
It's like when, are we talking like completely implode, like gone, or?
I'm talking about something that is combustible but not necessarily flammable. Aluminum?
No, those are not, never mind.
Like, yeah,
Those are flammable.
That's right above Abby's head. It's the chemical she did last week. That thing, right? It's azide. it will explode without having to put a fire next to it. So combustibility and flammability are not the same thing. Okay? Something can be willing to explode because you put a flame to it, or something can be willing to explode because you put electrical charge to it, or something will explode because you just gave it some friction.
I thought you meant like it won't cause fire when it explodes, which confused me.
No, sorry about that. Conductive. What are two things you can conduct?
I'm trying.
Electricity.
Conduct?
Well, the makers, what
What do you mean conduct?
conduct.
Electricity.
Like heat.
If you can conduct electricity and
Heat.
Good
heat,
word.
fantastic. So things when they're conductive, if they are usually conduct heat, they usually conduct electricity as well. Those kind of go hand in hand for most things. So conductive means, does energy flow through it easily? Could be heat or electrical energy. Okay? So chemical change is a change in the chemical structure of the matter. So usually burning, fizzing, bubbling, changing of color, new substances formed are all indicators of a chemical change. Alright? So we're going to do some chemical changes this week. You're going to mix two things together. Probably going to see some bubbling and fizzing. You're going to see that happen. Alright? You good here? Alright. Fantastic. Alright. Salt. What are some physical and chemical properties of salt? So give me some physical ones.
It's white.
It's white,
Powdery.
powdery, alright, crystalline.
Yeah.
Alright,
You said taste was between, but it's bitter.
salty, right? Salt's salty. Okay. What does salt like to do in water?
Salt is the bottom.
Dissolve.
Dissolve. What do we call that? We just talked about it. Solubility. Ready, Dawson?
Yeah, sure.
So, salt likes to dissolve in water, so it's soluble in water. If I take that pot of water and boil it, boil all the water out of it, what's left at the bottom?
Salt.
Salt. So, why is solubility a physical property and not a chemical one? Is because, does salt change what it is when it's in water? No, because when you boil the water back out, you have salt again. If you boil the water out and then you get something else, then it'd be a chemical change, but it's not. So the reason it's a physical property of solubility is because when you take that water or that liquid back out, you have your original substance again. Does that make sense?
Is that cold?
These are tires, rubber. Okay. All right. So let's talk about some chemical physical properties of rubber, of tires. Aubrey, you ready?
Yes.
Give me a physical property.
They're bouncy.
They're bouncy, absolutely. You can test that property without trying to change it. Fantastic. All right. Can you give me a chemical one?
A chemical property?
Yes.
They're conductive.
What do they conduct?
Air. That's not what
Usually when you're conductive, you either conduct heat or electricity.
they conduct heat and electricity, couldn't they?
Now, if I put rubber gloves on and I go deal some electricity, you won't get shocked.
Oh.
So what happens if we say if it does not conduct, we call that
Non-conductive.
non-conductive. Fantastic. There we go. You ready?
Yeah.
All right. All right.
I got it.
That's brilliant.
Yeah. What we got for me? Oh, fantastic. Thank you. I'm trying that microphone out today. Not that one. Okay. Let's do some gold. Amy, you think you got it? Think you got it?
Got what?
Gold. Give me a physical and chemical property of gold.
I don't know.
You can use your paper right in front of you to reference it, okay? Physical properties are observed using your five senses or without attempting to change it. So what's a physical property?
I don't know.
What's the color of it?
Oh. A gold.
Gold, fantastic. If I have this big old brick, gold gold. Why is that hard to say? Brick of gold. Man, it's Monday. If I got a brick of gold, what is it probably going to be? It's really heavy, right? Because it's a big density. That's physical properties. Fantastic. And did you know that there is gold in your phone?
Yeah.
Yeah, very, very small amount of it. Because what does gold do really, really well that rubber can't?
Conducts.
Conducts what?
electricity.
Fantastic. There we go. Way to go, Amy.
You got stuff.
Ready, Amy?
Getting something for that?
Absolutely. All right. Even if you don't fully get there, you're attempting to answer the question, is what's the whole point of giving a reward. Okay. All right. You're Smarties or dum dum.
No.
Okay.
Anna, did I tell you what I did?
We're gonna break all the
All right.
suckers.
So, physical properties observed using your 5 senses. Chemical properties are usually observed by attempting to change the substance or testing it. If we run electricity through gold, do we change it? No. But were we attempting to change it? Kind of. After a while, your phone gets old. All right, that gold gets corrupted, battery gets corrupted. All right, gasoline. Smells, absolutely. Smell would be a physical property. All right, the odor it releases. Is that an argue also with taste? Absolutely, but I'm going to call it a physical property.
Let's not taste it.
Like smell and taste.
Yeah.
Because technically, before you smell something, there's a chemical reaction in your nose, or if you taste something, there's a chemical reaction on your tongue. All right, we're going to call it physical though. Let's say this. Ready? Physical property, smell, absolutely.
It's orange, it's like a weird looking.
It's that weird little tar color.
Yeah. Well,
Alright.
actually, it's not really that.
Chemical property of gas.
You can really gas. It's like,
Yeah.
it's weird.
You can look at the list in your notes right now.
Is it for me?
First one on the list.
Oh.
Flammable, right? Take a match.
Even Kinsey got that, Kingston.
Alright? Absolutely.
No offense.
Okay? So when it comes to chemical and physical properties, okay, there's not going to be like this huge major list I want you to memorize, but I want you to understand, really understand. Physical properties are observing typically using your 5 senses or testing the material without attempting to change it. So if you want to measure the density of gold, you'd measure the mass and the volume. Would you try to change that gold? No. All right? If you wanted to see if it was flammable though, what would you do? You would attempt to change it, put a flame up to it, find it's non-flammable.
Could you catch gold on fire?
No, you could melt it,
And then you get liquid gold.
and then you would get liquid gold. All right. When chemical changes happen, the law of conservation of mass is always observed. All right. Don't worry about the numbers on the picture. All right, the numbers on the bottom of the picture. Don't worry about these. We're gonna talk about that later. That's like a end of the semester kind of thing. All right. Law of conservation of mass says matter cannot be changed or destroyed, or created or destroyed. It can only be changed. All right. The atoms inside are what are rearranged. So we're gonna take what we did last week with atoms and molecules. So here's what I want you to be able to see and kind of understand with this picture. If I take methane, which is a fuel, and I burn it in the presence of oxygen, it will produce 2 products, carbon dioxide and water. I will give that to you. I will tell you what the reaction is and what it produces. All right? Your job is to balance the reaction, to figure out how many molecules and atoms of what you need on both sides. Okay? We'll get to the point where we'll predict reactions, but that's like one step at a time, okay? But the law of conservation of mass says mass in equals mass out.
Do you want us to draw the atoms?
Yeah, you just put little circles though. Okay? So how do we read this? You'll be given CH4 plus 2O2 gives you CO2 plus 2H2O, okay? We're going to go through a little bit how to read this, all right? But law of conservation of mass says matter cannot be created or destroyed. You only rearrange those molecules. So very simply said, mass in equals mass out. Yeah,
Did someone say that?
what?
Like, so, like, you know how you have to memorize, like, Newton's laws?
Mhm.
Like, who wrote that law?
I wrote this one because the true law is super wordy. But a law is different than a theory. A law is true in every instance. So law of conservation of mass saying mass is always conserved. A bunch of scientists got together. There's like a really famous picture of like all these scientists getting together, and they said, you know what? We agree, we concur. Collectively, they agreed.
Okay.
However, if you're the one scientist to discover something, usually it has your name attached to it. So Newton's laws of motion, who put those into action? Sir Isaac Newton.
Does that say 2H2O?
Yes, 2H2O.
So who put this into motion?
This was just a bunch of scientists got together and they all agreed uniformly
Does it say
together.
water? We're gonna say it's. So this is 2H2O.
Just 2H2O. Okay. All right. Don't write it down. Just black, right?
Thank you.
So what's going to happen is you're going to be given a chemical reaction. You're then going to predict how many molecules and how many atoms are on both sides. Okay? Here in your head, when we're balancing chemical reactions, here's what I want you to see. What's going in yields what's coming out. But do we see how in this first picture on the top side, there's only one oxygen atom on the right and there's two on the left? So this does not follow the law of conservation of mass. However, if we change the ratios of what pops up and how often they pop up, we can then say not only are the elements on both sides the same, but so are the atoms. Cool? That's it. That's all we're gonna do when we balance chemical reactions. Alright? But we have to do some specific vocab before we start balancing reactions. Alright? On the left side of the chemical reaction is your reactants. That's whatever you're mixing together. That's whatever your chemical reaction is. Lighting something on fire, mixing two liquids together, boiling something to a chemical reaction. Right. Yields is the arrow. All right. So right now it's always going to go to the right. There will be a point where we draw the arrow also going both sides. Right. But yields or gives you your products. So reactants, yields, products. Mackenzie, I promise you, we have one more slide of text. And we'll do a couple examples and we're done with those.
Then what do we do?
Homework? Or just get started in the lab. We'll see. See how quickly we get through those examples.
What is Rxn?
Reaction.
Alright.
It's just a shorthand annotation for reaction.
I'm just gonna I have enough money
Are we down to do 2 labs this week?
Are we down?
Depends
to
on
it?
how hard they are and how much
Yeah.
time they're gonna take.
Honestly,
I'm-
I'm good.
We did one,
As long as
like,
there's no
every
reading.
5 weeks or lab.
We're
Yeah,
doing one
we
lab a
usually
week
do
at a
labs.
minimum, unless something goes wrong for my supplies. But I really
As
want to
long
do
as
2
we
labs this
manage
week.
to get it all done.
Because one applies to chemical reactions, the other one applies to chemical physical properties. So I would love to do both. Alright?
Yeah.
And before I forget, I'm pushing your test back a week
No worries.
because 1, it's homecoming week. You guys will be doing a bunch of homecoming stuff. And 2, I want to really make sure we've nailed down balancing chemical reactions before we take the test. Okay? So I'm pushing the test back, but we're also adding another week of stuff on. So that tells you, since the test covers more material, the questions won't be as difficult. There'll be more questions, but not as difficult. Okay? Alright. Law of conservation mass must be observed. Atoms in equals atoms out. Elements in equals elements out. When you're balancing chemical reaction, you have to follow this route.
What, Aubrey?
What?
Say that again, Aubrey.
Can we have that in English?
Does Rxn stand for reaction?
Absolutely.
Dang.
What did you think it standing
Rx is prescription. But it's written like this.
That?
That is prescription.
That's what that was.
Studied the pharmacy for a little while. Alright. Atoms in equals atoms out. Elements in equals elements out. Okay? we're ready to hop on straight to an example. You ready?
Wait, is this the last one we
No.
have to write?
It depends on how smoothly the examples go. If we're stumped on them, we'll go back. If we blow through it and we understand what's going on, we're looking good. Yeah, Dallas, what's up?
I was gonna say if you could like move to the left of it, thank you.
Absolutely.
Got it done, Aubrey. It's on my paper. You can look off my paper.
We ready?
Yeah.
All right.
Aubrey, you can.
Okay.
Oh my gosh, I thought we were gonna.
If this goes smoothly, and this goes well, I don't need to go back. Okay? Because everything I'm about to explain is on that previous slide. Okay? When you're balancing chemical reaction, the first thing I want you to do, if you've been taught another way and you really, 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 really like that way, I'm not going to fight you. But those other ways that I've seen it, I find to be less helpful because you end up doing twice the amount of work what we're doing half the time. All right. First thing you do in a chemical reaction is I want you to write the elements you have down the middle. We got nitrogen and hydrogen. All right. So there we go. Half the battle's already done. We know the elements on the left side and the elements on the right side are the same. There's nitrogen on the left, there's nitrogen and hydrogen on the left, nitrogen and hydrogen on the right. The next thing we need to do is just count what we have.
You're not gonna finish your hydrogen.
Absolutely. I want to call Mary Kate though, so we can get her some candy. Okay. Mary Kate, ready? It's gonna be super easy questions. All right. How many nitrogens do I have on the left side? On the left side. Two. Woohoo! Hard stuff, right? How many hydrogens do I have on the left side? Two. Tough stuff. How many nitrogens do I have on the right side? If there's no number here, it's understood to be a 1. So how many nitrogens do I have? 1. And how many hydrogens? 3. Fantastic. All right. I'm moving on so you can breathe. All right. Who am I going to call next? I think I'm going to call Abby. She's been too talkative all day. Ready, Abby? Am I balanced? No. We got to balance the nitrogens and the hydrogens. Here's what I'm going to say. Typically, balance hydrogens last. Balance hydrogens, try to do it at the very last. Because there's so many of them, and if you try to balance hydrogens and there are multiple things, you're going to run in circles. Try to balance hydrogens last. So let's balance the nitrogens first. Do not do this. Do not just put a little 2 right here. You can't change the molecule. You can't do it. Instead, what we can do is change the number of those molecules we have by putting a 2 out in front. Follow me there? It's still NH3, but now I've got 2 of them. So Abby, how many nitrogens do I have on the right side? 2. Whew. But did that 2 also affect anything else?
Yeah.
Absolutely. The number of hydrogens. So how many hydrogens do I have? Fantastic. I got 6 hydrogens. You want to call it quits here for a dum-dum, or do you want to take us all the way there, be done, for a piece of chocolate?
Are we getting chocolate? That's a whole new level of blue.
You think you got it for the rest of it?
Oh, what?
I tell you what, you can shoot for it, and if you get it wrong, you get a dum-dum. If you shoot for it and you get it right, you get a piece of chocolate. Can we do that?
Yeah, it's red.
All right. Are my number of nitrogens balanced? Shh. Yes. So am I going to change this number? No. If it's nothing there, it's understood to be a 1. We're going to keep that 1 there. However, what do you want to put in front of hydrogens to get you what you need? A 3, because 3 times 2 is? Fantastic. All right. Your options for chocolates are Kit Kat or Reese's?
You keep
Reese's. Okay.
Oh, look, look.
I like your flip-flops.
Thanks.
Somebody first period after Reese's doing, they caught it super hard and like smashed it. I'm like, sorry man, sorry about you. Okay, Do I have the same elements on both sides?
Yes.
Yes. Do I have the same number of atoms on both sides?
Yeah.
Yes. So what are my coefficients and what are my subscripts? So let's use that vocab from the previous slide. Your coefficients are the numbers that go out in front. All right. Coefficients are you found in math. Usually when you put them in the beginning of a variable, it's your coefficient. Coefficients go out in front. Your subscripts tell you how many of that element you have in that molecule. So the coefficients you can change. All right. But the subs, you leave alone. Because if you change the subscripts, you're changing the molecule. Right? If you change the coefficients, you're changing how many numbers of that molecules you have. Looking good? Looking good, Mag?
Yeah.
Cool. All right. As you can tell, if you're like laser focused in or you're just spaced out.
I was spaced out.
All right. Can you help me for the next one? Can we get you some candy? Okay. All right. This looks crazy, right? It's not going to be that bad. First step is what? Unbalanced chemical reaction.
You write the elements down in the middle.
Absolutely. So we're going to write Na, all right, capital N, lowercase a. Because that's sodium, anytime you see a lowercase letter, we know it goes with the element before. Okay? What I have seen some people do, we'll do this. They'll go N, A, and what they'll do is they'll look on the periodic table. Hey, Mr. Williams, where's lowercase a at? I'm like, there's no lowercase a. Anytime you see a lowercase, all right, it fits with that element. So we got Na. What else do I have? Sulfur, fantastic. That's. You can just tell me the letter, okay? What's H? Oh, sorry, I said it for you. All right, and the last one. What's the last element I got?
The element or the letter?
Just some of the letters.
CL.
Cl, okay? Which is chlorine. Fantastic. All right, come on. Here we go. All right. We got elements listed. We're looking good. All we need to do is we need to count them down. Oh, by the way, I got 2 different types of dum-dums. So I have like 10 different flavors. I got new flavors I never had before, like birthday cake. Would you be interested in a birthday cake dum-dum? Okay. There's birthday cake. There's like a slushy one. There's a blueberry blast. Caramel apple. Caramel apple, if you want to pronounce it wrong. All right. Span, I haven't picked on you yet?
That's wrong.
No, you ready?
Yes.
I think I picked on everybody.
What? What do you want?
I think so. All right, ready? How many sodium, how many NAs do you have on the left side? 2? Sulfurs? Hydrogen? Chlorine? Woohoo! Tough stuff. All right, let's do the right side. Fantastic. Whoop. Am I balanced? No, I sure am not. You go with the classic blue raspberry? You don't like Dum-Dums? What do you like? Smarties? Sure. I mean, you don't have to have the candy.
I mean, I like Smarties.
Sure. I would say you are what you eat, but then I also give out Dum-Dums too, so that doesn't really apply. Dawson, you ready? I've already picked on you. You got candy in your mouth. I already picked on Kingston. I didn't give you a piece of candy yet. You gotta earn it now. Alright, King, help me out. What am I gonna do? Am I balanced?
No, you're not balanced.
Nope. So let's go to the sodiums or the NAs on the right side. What am I gonna do? Can I-
Put 2 in front of that.
Can I put a 2 right there?
No.
Nope. And put a 2 out in front.
God dang
How many sodiums do I have now?
2.
2. But does that change anything else?
Yeah, that changes the CL.
Changes the chlorines because that Na and Cl are put together. So we have our 2 chlorines. Cool. Looking good so far. Am I balanced?
Not yet.
No. What am I gonna do?
Put 2 in front of the HCl on the left.
Absolutely. This gives me how many hydrogens?
2.
How many chlorines?
2.
Nailed it. Am I balanced now?
Oh,
Absolutely. Okay.
Don't do that. Do it underhand.
Oh, nail
I
it.
can't really do it underhand because I'd have to get really high to do that. And then
You
hit
could
the
just make
ceiling.
it a long underhand, like a shooter.
I'm not a softball player. I don't have this.
He went to the softball.
Aubrey, if you let it go
I don't have the
sooner,
technique down.
higher the ball goes.
Okay, I don't push on ball.
All right. This is probably the tricky one. This is probably the tricky one. Your homework has one something similar to this. Okay.
Like down here. Or up here.
Aubrey, if you release it up here, ball goes high.
Most of us.
You let go of it down. Goes below.
That's what I'm saying. You said you had to line it.
Most of us could list these elements and they're looking okay. Here's the thing I run into though. And here's what I recommend. Alright? If there's oxygen involved, that one goes after hydrogen. So balance all the other stuff out first, then the hydrogens, and then the oxygens, and you tend to find yourself at equilibrium a whole lot easier. If you try to balance oxygens first, do you see how oxygens are in two spots right here? You're not going to know which one to change. You're not going to know which number to change. However, since carbons are only one spot, right, we can go carbons first, and then the rest of it kind of makes sense from there. All right. Let's try this out. Annie, think you got it?
No.
No?
No, I like low-key don't get this.
Okay. All right. At what point are you getting stumped at?
I think I just don't know like why you can change certain stuff, but you can't change others.
So for like, that's a perfect question. So I'm gonna take a step back, and this is water right here, right?
Yeah.
Well, this is H2O. 2 hydrogens, 1 oxygen. Good there? What I can't do is I can't just say, hey, if I need another oxygen, I'm just going to tack another oxygen onto it, because is that still water?
But then why can you add the 2 in front?
Because what I can do is if I need more oxygens, what I do is I just create another oxygen, another water. Follow me there?
Yeah.
Okay. If I need more oxygens, we throw in a second water. If I need more oxygens, I can't just tack on an oxygen because that turns it into hydrogen peroxide. All right. You just played God. You changed the molecule. All right. You can't do that. You can't just throw in a 2 here because you feel like it. All right. You're changing what's happening. What we can do is change how often it shows up. So if I need 2, we'll have 2 different molecules. All right. But I can't change what's inside of it. That's a big no-no. Cool? Does that help a little bit?
Yeah.
All right. Matt, yeah, Maddie?
Well, isn't that what the product side?
Yes.
How can you change it out of it and look at it?
It's the ratio of how much is produced. Right now, we have 3, 8, 2, 2, 1, and 3. These ratios are wrong. And how do we know they're wrong? It's because the number of elements on both, or atoms on both sides are not the same. Follow me there?
So how do you, why would you need to do this though? Because if you, if it's like an actual chemical reaction, then wouldn't it have the same atoms no matter what because of the
This
law?
is an unbalanced chemical reaction. The ratios are not right of how much is going in versus how much coming out. Law of conservation of mass says the number of atoms in equals the number of atoms out. You can't break atoms.
So that could never actually happen.
Well, this is unbalanced, and then we're going to predict what really happens.
I'm gonna have to see unbalance.
So like this one right here, what we just did, we had Na2S plus HCl, right? Actually, you know what? Let's go back to the first picture. Because this one's color-coded. Unbalanced, here's where you're at. How do we read this? This is H2 plus O2 gives you H2O. That's the way this top one is reading. Follow me there?
Wouldn't it be H2O2?
There's no second oxygen there.
But there's right there, no, I'm confused.
Those here, that's where the O2's at.
What? What?
Okay, so let's just take a step back. Here's the problem we run into. If you have to pay attention or you check in, check out, I have a really hard time with following it. So, Maddie's question. I'm trying to answer Maddie's question. Right? When it's unbalanced, we do not have the same number of atoms on both sides. Follow me there?
I get that.
Okay.
But like, that can never physically happen, right?
Correct. This won't happen. What will happen is the ratios of how much they show up in will change. So this is 2 H2s plus O2 gives you 2 H2Os. Follow me there? So what we have to do is taking an unbalanced chemical reaction, count the number of atoms and elements and all the good jazz we've been doing, and then predict the ratio of what they're going to show up in. Does that help?
Yeah.
Okay. All right, Hannah, your turn. What's up?
So like, if we were scientists in a lab,
Yes.
we were trying to make water by combining H2 plus O2
Mm-hmm.
to get H2O.
Mm-hmm.
We would get water either way, so why does it need to be balanced?
You would get water, but one would run out a whole lot quicker than what you're expecting. Like if I'm going to go build go build bicycles, all right, and I have 100 tires and I have 100 bicycle frames, what am I going to run out of first?
Tires.
The tires. I need 2 times as many tires as I do bicycle frames because the ratio is 2 to 1. Follow me there?
Yeah.
So if I want to make 100 bikes, I need 200 tires. Follow me there?
Yeah.
Same thing here. If we want to make 100 molecules of water, we need twice as many hydrogens.
Okay.
Follow me there?
Yeah.
We are actually going to do that. We're not going to create water. We're going to take water and we're going to shove a bunch of electricity through it, and we're going to create hydrogen and oxygen.
Okay.
It's called the electrolysis of water. We're going to take that and we're going to separate it. And what you're going to see is you're going to produce twice as much hydrogen as you do oxygen. And then we're going to light the hydrogen on fire. Okay?
So if
Perfect
Right.
questions. Here's what it says. There's no such thing as a dumb question. And if you have that question, I'm going to bet somebody else in this room has the exact same question. Okay?
So why would anyone ever use the unbalanced form instead of just memorizing the already balanced form?
Because these chemical formulas will get really, really ugly, and you can't just memorize them. We'll also get to the point where I give you your reactants using the chemistry we haven't learned yet. You're going to predict the products. Now we know this one would be H2O. That's chemistry we haven't learned yet, and we're not going to learn for a little while. You're not going to predict the products, but you're then also going to balance it, and then tell me the ratio of what shows up. A more complicated one would be something like if you have this chemical reaction, predict what happens, which you're not doing right now, but we're going to get to at some point. And then balance it. I'm just taking you all the way back to step 1. I give you this. All you need to do is balance it for me.
Okay.
Cool? We will get there, absolutely, but it's like we need to know a lot of chemistry before we get there. Okay? So, back to here on this one. Are we good? Thumbs up, thumbs down, not middle fingers. Okay. Are we good on just balancing it though? Are you like,
Oh,
good?
you said no middle finger. But you're doing. I'm confused now.
This one.
I don't think I
All right.
did it like this when he said it. It's not
You
like
can try the homework out tonight. If you have questions, absolutely bring them tomorrow, okay? We'll do more one-on-one questions. Hannah, you get the gold star for asking questions. I really appreciate it. Okay? Same thing for you, man. Okay? And I understand that this, but the chemistry knows like here, and so rather than giving you this much chemistry and being overwhelmed, we're giving you this much chemistry, and then next week we're gonna go a little bit wider. And then at the end of the year, you'll be like,